Good morning, students, and welcome to class today. I trust you are rested well and ready to learn. Today we are going to be studying differentiation from first principle. This is one of the most important topics in calculus. If you are able to learn differentiation from first principle, then on your own you will be able to derive all forms, all functions of differentiation, all formulas, general forms, the transcendental functions, even the rules like your product rule, quotient rule, you'll be able to generate them on your own. So differentiation from first principle is very important. Let's get into it. In this class, we are going to aim to understand what differentiation means, state the formula for differentiation from first principle. We are going to learn steps to differentiating from first principle, and we are going to solve examples on differentiation from first principle. Now, what is differentiation? For definition's sake, differentiation is the branch of mathematics that seeks to study the rate of change in functions and quantities. However, what does this really mean? To understand what this means, we are going to look at the origin of the principle of differentiation. The principle of differentiation was developed from the principle of finding the gradient of a straight line in coordinate geometry. Now, when we want to find the gradient of a straight line, what do? Having a straight line, we take two arbitrary points, A and B, anywhere on this line. We take the change of the value in y, that is our y2 minus y1, divided by the change of value in x, x2 minus x1. When we divide this, whatever we get gives us what is known as the gradient of that line. And that tells us how much change we expect in y for any given change in x. Now for a straight line, this gradient is always constant. However, if our graph is a curve and not a straight line, then how do we find the gradient? In this case, the gradient is not a constant anymore. So at any point that we want to find the gradient, we need to use a tangent of the curve at that point and find the gradient of the tangent. However, looking at this graph, the tangent at this point will be different from the tangent at this point, and that will be different from the tangent at this point. This tells us that this tangent or this gradient is related to the value of x. It changes according to the value of x, which means it can also be a function. Finding the function that gives us this tangent is what is known as differentiation. In order to differentiate a function with a known algebraic equation or an algebraic expression, we use this formula. The y dx will be equal to the limit of change in x tending to 0, f of x plus change in x minus f of x all over change in x. Now, what does this formula mean? I'm sure it looks confusing, but this formula is basically the formula for gradient of a straight line. This is our y2 and this is our y1. Change in x is simply our x2 minus x1. Simply means a change in x. So when we change our x, we expect a corresponding change in y, and that is what this f of x plus dx means, or f of x plus change in x. That's what it implies. So when we change our value, whatever value we added to x, to change it from x1 to x2, this will be the value of the change in y because of the x2 that was added, and then this will be the original value of y1. So this is simply the formula from coordinate geometry. But to understand it better, let us delve into the examples and see the step-by-step, the generation of this formula and how to use it in solving. Now, these are the steps to differentiating from first principle. Our first step will be to state the function in an algebraic equation. Y equals to f of x. So if you have a graph, for example, you will need to state in this form. If you are just given an expression and told to differentiate, for example, you are told to differentiate x squared, you will need to write it in the form y is equal to x squared. That will be your first step. And the second step will be to add a change in x to your and a corresponding change in y. We are going to understand this more during the example, but whenever we add a little value to the x, we expect that there should be a corresponding change in y. That's what makes it a function. Our third step will be to expand the right hand side of the equation. So whatever function we have for the x, we will need to expand it and separate each of the terms. That will make the operations easier for us. We'll subtract y from both sides, divide through by change in x, and then finally find the limit of the function as change in x tends to 0. Whatever we have left after following all the steps above will be the derivative of the function. So to understand it better, let us look at an example. Here we are given the example y is equal to x cubed. The first step will be to add our change in x and a corresponding change in y. So this value says y equal to x cubed. If there is going to be a change in x, remember, whatever value we have in this x is inclusive. So if x is 2, that means x cubed will be 2 raised to power 3, and that is 8. If x is 3, that means x cubed is going to be 3 raised to power 3, and that is 27. So if we are going to be adding anything to the value of x, let's say our x is going to be 3 plus 1, giving us 4. This is not going to be 3 cubed plus 1. No, that's going to be 3 plus 1, 4, all cubed. Right? So coming to this, that's why we have this bracket. X plus our change in x cubed. Whatever value is going to be, because if we had x equal to 2, for example, our y in this case is going to be 8. But when x increases from 2 to 3, y is going to increase from 8 to 27. So this change in y here captures that change from 8 to 27. That is what this line means. Y plus the change in y, which corresponds to the change in x that we just added. Y plus change in y equal to x plus change in x, all cubed. We need to find this, and then our next step says that we expand the right hand side. So this change in x plus change in x cubed, we are going to need to expand it using either your binomial theory, your Pascal triangle, or simply multiplying. We'll get the expansion of this to be all of this. And that means y plus change in y is going to be x plus x cubed plus 3x squared change in x plus 3x change in x squared plus change in x cubed. Our next step says subtract y from both sides, remembering that y is equal to f of x. So subtracting y from y minus change in y and subtracting y from this side, we are going to get this minus y. But if y is equal to x cubed, then we change the y here to x cubed, giving us this function here. When we have plus x cubed here minus x cubed, both of them will cancel out, leaving us with 3x squared change in x plus 3x change in x squared plus change in x cubed. Our next step says divide through by change in x. So if we divide change in y over change in x, dividing this, change in x will cancel change in x. Change in x here will cancel one of the change in x here, and change in x will also cancel 1 out of here. So we are going to have 3x squared, 3x change in x, and then change in x squared. Now finding the limit of this function as change in x tends to 0. The limit of change in y over change in x as x tends to 0 is our derivative dy over dx. Now let's look for the limits of these functions independently. The limit of 3x squared as dx change to 0 is still 3x squared since there is no change in x here. So the limit will changing x tending to 0 will not affect it. In this case, 3x multiplying a number that is going to 0 will give us 0, because any number multiplied by 0 is 0, and the same thing applies here. So our change in y over change in x in this case, or our dy dx or derivative, is going to be 3x plus 3x times 0 plus 0 squared. And so the derivative of y equal to x cubed is going to be 3x squared. I hope you were able to understand this today. Here are some practical exercises. I expect that by the time I expect that you will use 10 to 15 minutes to solve all of this on Google Classroom. I'll be grading you soon. If you have any questions, feel free to ask me. Thank you for watching and have a great day.